Hello, good day. This is Samuel Adekan, also known as Edisam. Welcome you to this lesson. So we'll be looking at a specific capacity, method of mixtures calculation. So please, if you're not subscribed to this channel, go ahead and hit the subscribe button and like the video. Thank you so much. So let's head straight away to the lesson. Hello and good day. This is Samuel and I can welcome you to our physics lesson on specific capacity. This is actually our third lesson. In this lesson, we will solve some calculations relating to specific capacity. We started calculation in the previous video. We've actually solved one problem, so we're going to solve more today. So please, if you're not subscribed to this channel, make sure you subscribe and like the video, and you can share the video with others or your friend. So we are looking at the topic specific capacity. Like I said, if you missed our previous video, make sure you go back and watch them. So we're going to solve this question here, which states that 20 kilograms of a metal at 100 degrees Celsius was dropped into 80 grams of water at 15 degrees Celsius in a calorimeter of mass 80 grams, made up of the same metal. If the final temperature is 18.4 degrees Celsius, calculate the specific capacity of the metal. The specific capacity of water is equal to 4,200 joules per kilogram per Kelvin. So a metal of mass 20 grams. So let's start solving. We'll bring out our parameters. The mass of metal, let's call that M, is equals to 20 grams. This is same thing as 20 divided by 1. We want to convert it to kilogram. The mass of the metal from here, 20 grams of metal. The mass of the metal is 20 grams. I want to convert it to kilogram, so I divide by 1,000. Remember that 1 kilogram is equals to 1,000 grams. That's why I'm divided by 1,000. So 0 cancels 0. At the end of the day, if you divide this, you're going to have 0.02 kilogram. Okay. So what was the temperature of the metal? Initial temperature of the metal equals to 100 degrees Celsius. Okay, 100 degrees Celsius. Then was dropped into 80 grams of water. So mass of water is equals to 80 grams. This is 80 divided by 1,000 kilograms. This is going to be 0.08 kilograms. If you punch this on a calculator, you're going to arrive at 0.08 kilograms. Even if you do it manually with that calculator, you can actually solve it. How? You have 8 over 100. So how do you solve this? You have 2 zeros. So just write your 8 here, put a point here, put 0 here, put 0 here. So you have 1, 2. These 2 zeros here. You can't backward and you have 0.08 kg. That is that. So the mass of water is 80 grams. Into 80 grams of water at 15 degrees Celsius. That means the temperature of the water was 15 degrees Celsius. Initial temperature of water equals to 15 degrees Celsius. Let's give this as theta W. Initial temperature of metal let's do that theta m. Okay, so 80 kilogram of water at 50 degrees Celsius in the calorimeter of mass 80 gram. Mass of calorimeter so I'm picking out the parameters. Let's call this m sub c. Mass of the calorimeter is 80 gram, which if we divide this by 1000 it will still give us 0.08, just as here. Okay, mass of calorimeter is what? 80 gram, which is 0.08 kilogram. So since water was added, water was contained in the calorimeter, and the temperature of the water was 15 degrees Celsius. So that temperature, the water will transmit is heat to the calorimeter. The calorimeter is going to have the same temperature as the water inside it, whatever is inside it. So the temperature of the calorimeter is, initial temperature of calorimeter is also 15 degrees Celsius. Okay. If the final temperature of the mixture is 18.4 degrees Celsius, final temperature of mixture is equals to what? 18.4 degrees Celsius. Calculate the specific capacity of the metal. So we have to get the specific capacity of the metal. The calorimeter is made of that metal. The material that is used to make the calorimeter is made of the same metal. So that means the specific capacity of the metal and the specific capacity of the calorimeter are going to be the same. Since the calorimeter is made of the material of that metal, they are going to have the same specific heat capacity. So we go ahead to solve. Like I said, we're going to use the method of what? Of mixture, which tells you that heat gain is equals to heat loss. As far as heat gain is equals to heat loss, based on the method of mixture, so we can actually proceed and solve this question. Okay, so let me rub off the question itself to have space to solve it. So heat gain is equals to heat loss. It's simple as heat loss is equals to heat gain. So which of the substances is going to lose it? Which one is going to gain it? So let's look. Temperature will give us an idea. The initial temperature of the metal is 100. The initial temperature of water is 15. The initial temperature of calorimeter is 15. Is lower. So at the end of the day, when the metal at 100 degrees centigrade is added to the water in the calorimeter, the water will acquire heat. It's going to absorb heat from the water. Thereby, the temperature will rise from 15 upward to the final temperature of the mixture, which is 18.4. When the metal is dropped into that, when that metal is dropped into the calorimeter containing water, the temperature of the metal is going to drop down till it gets to the 18.4, which is the temperature of that mixture. Okay, so the metal is going to lose it. It's going to lose it, while the calorimeter and water are going to gain it. So heat loss by metal, let's calculate that. Is given by mass times specific capacity times the change in temperature. So the mass here is 0.02 kilogram. The specific capacity is what we're looking for, of the metal is what we're looking for, we don't know it. So So we use the C. We represent that by C. Then the temperature change. The initial temperature of the metal was 100. The final temperature of the mixture was 18.4. So it's going to be the higher one minus the smaller one, which is going to be 100 minus 18.4. Okay? So 100 minus 18.4 gives us 81.6 times C times 0.02. Okay, so at the end of the day, we have when we multiply 0.2 times 8.1, we land at 1.632 C. This is in joules. So we have 1.632 C. C is unknown. So this thing is not completely solved. We are looking for C. So we leave it this way: 1.632 C. This is small c. Joules. This is the heat lost by the metal in cooling from 100 degrees Celsius to 18.4 Celsius. Okay. So heat gained by water, or let's look at, yes, by water, yes. It's gained by water. It's gained by water is given by the same formula, MC change in temperature delta theta, M times C times change in temperature. This is means M times C times change in temperature. That is the mass times the specific capacity times the change in temperature. So the mass of water was 80 gram, which is 0.08 kilogram, times the specific capacity of water, which is 4,200 joules per kilogram per Kelvin, times the change in temperature. Initial temperature of water was 15. Final temperature of the mixture was 18.4. So this is going to be 18.4 minus 15 degrees Celsius. So this is going to be 0.08 times 4,200 times 18.4 minus 15 is 3.4, which at the end of the day, when we punch our calculator, what is that going to give us? That is going to give us 1142.4 joules. Okay, this is going to give us 1142.4 joules. So this is the heat gained by water. Now the calorimeter, which also contains water, is also going to gain heat. So heat gained by calorimeter is equals to the same formula, MC change in temperature, difference in temperature, mass times specific capacity times the change in temperature, the difference in temperature. So the mass in this case of the calorimeter is 0.08 kilogram. The temperature, the specific capacity of the calorimeter, we don't know, is still the same material as the metal. So we're still going to use C. The C we use there, we still use it there, times the change in temperature, which is still the same thing as water. The calorimeter water experience the same change in temperature. So we have 18.4 minus 15. This was the final temperature of the mixture. This was the initial temperature of the calorimeter. So at the end of the day, we have 0.08 times C times 3.4. So 0.08 times 3.4, what do we have? That gives us 0.272 C, still in joules. Still in joules. Okay, so I rub this off. So at the end of the day, the method of mixture states that heat loss is equals to heat gain. So heat loss by the metal is equals to the heat gain by water plus the heat gain by the calorimeter. So we are going to put that in the expression. So heat loss by the metal, which is 1.632 C joules, is we have this as 1.632 C joules is equals to the heat gain by the water, which is 1142.4 joules, plus the heat gain by the calorimeter, which is 0.272 C. So we collect like terms, we move this to the side, it becomes 1.632 C minus 0.272 C equals to 1142.4. When you subtract this, what do you have? This gives you 1.36 C equals to 1142.4. So now we are going to solve for C. How do we solve for C? We have to divide both sides of the equation by 1.36. So you have to do away with this 1.36. The only way you can do away with it. So this thing is the same as 1.36 times C. So since C is being multiplied by 1.36, to do away with 1.36, you have to divide, do the opposite of multiplication. So you divide it by 1.36. So you have 1.36 C divided by 1.36 equals to 1142.4 divided by 1.36. So 1.36 cancel 1.36. This C is equals to, okay, let me do it over here. C is equals to 1142.4 divided by 1.36 gives us 840. So the specific capacity of the metal is 840 joules per kilogram per Kelvin. We have 840 joules per kilogram per Kelvin. This is the value for the specific capacity of that metal. So I hope this is actually understood. So we're going to move on to the next question. So right now we'll move to question 2. Question 2 states that a mass m of water at 100 degrees Celsius is added to another mass capital M of water at a temperature T, and the resulting temperature, that is temperature of the mixture of both water, is T. If the specific capacity of water is 4,200 joules per kilogram per Kelvin, derive an expression for T in terms of other quantities. So the first part of the water, this water, which of the water is at a higher temperature? Mass m of water at 100 degrees Celsius. Mass small m is added to another mass capital M of water at a temperature T. T and 100, which is higher? Which is higher? This capital T here of the mixture, where does it lie? So between 100 and small t, which is higher? So 100 is higher than that small t. Why? The reason being that water is a liquid, is a substance in question here. and the highest temperature of water is 100 degrees. When you boil water, when it gets to 100 degrees, the temperature doesn't increase anymore. It stays there. So this is the highest temperature that water can get to. So this is the highest temperature. This one is higher than T. So the temperature is going to be 100 degrees Celsius is greater than T. T is less than 100. So that means that the mixture will lie between T and 100. So this is the temperature of the mixture. This is the temperature of capital M of water. This is the temperature of the small mass M of water. This capital M, small letter m. This is temperature. These are their temperatures. So like I said that 100 is higher than this T, because water cannot, you can't have water at 120 degrees Celsius. It's impossible. Even 110, even 111, you can't have water at that temperature. At normal temperatures and pressure, at atmospheric pressure, you can't have that. So we are going to go ahead and solve. So that means this mass M water, mass small m, since it's at a higher temperature and mass capital M is at a lower temperature, when they are mixed together, the mass small m of water is going to lose heat, while mass capital M is going to gain heat. So based on the method of mixture, we are told that heat loss is equals to heat gain. So which is losing it? Small m of water. Small letter m, mass small letter m of water, which is gaining it? Capital letter M of water. This is one is at the temperature. Capital letter M is at the temperature of T, while small letter m is at the temperature of 100 degrees Celsius. The mixture is at temperature T. So heat lost by mass small letter m, this is going to be mass times specific capacity of water times the temperature change. That is the temperature of the initial temperature of that water minus the temperature of the mixture. So the mass of that mass of the liquid is small m. The specific capacity is of water is 4,200. So you put 4,200 here. Then the temperature change. The final temperature of the mixture is what? T. The initial temperature of that liquid was 100. So we're going to, since 100 is bigger than T, we're going to have 100 minus T. Okay. So we're going to have 100 minus T. So let's leave it this way for now. So heat. Now in case you want to ask me, how do I know that 100 is bigger than T? This fluid was at a higher temperature. The temperature of fluid of mass small m was at 100. Like I said, water can't go above 100. So that means when the two fluids are mixed together, the temperature is going to drop from 100 to a lower value. Okay, so this T is definitely smaller. It is lower value than 100. So heat gain by mass capital M of water, still given by M times C times delta theta. Now, I move to this other end to continue solving. The mass of the water in this side is capital M. The specific capacity, we are still dealing with water, so it's still 4,200. The temperature difference is delta Q. The temperature of that mass M was what? Small letter t. The final temperature was what? Capital letter T. So this is larger than small letter t. From this analogy, this is greater than small letter t. So you're going to have temperature difference capital letter T minus small letter t. So this is the heat gain by the liquid of mass M. This is the heat loss by the liquid of mass small m. So we're going to equate these two together according to the method of mixture. We have that this is 4,000 small letter m into 100 minus T. Sorry, 100 minus capital T. This is capital T is equals to 4,200 capital M capital T minus small letter t. So since this is on the left hand side, this is on the right hand side, so 4,200 can cancel 4,200 on the left right side of the equation, can cancel 4,200 on the right side of the equation. They can cancel each other. So what are we left with? We are left with M into 100 minus capital T is equals to M capital M into capital T minus small letter t. So we were asked to derive an expression for capital T in terms of other quantity. So we expand this. We have, if we expand this, what do we have? We're going to have 100 small letter m, m capital T, m capital T, m small letter t. So we're going to collect t to one side. We're going to collect the terms containing t, variable t, to one side. So I'm going to bring this minus m small m t to the right hand side. So we have 100 m plus, I bring minus mt to this side, it becomes plus mt is equals to m capital T minus plus small m capital T. I bring this is the minus here, minus mt comes over here and becomes plus mt small t, this one here. So this and these are adding together. At the end of the day, we have capital mt, small mt. So we can actually factorize out t. So you have t factorizing out. You have m capital M small m plus small m. So this is 100 small m plus capital M small t. So at the end of the day, what do you have? You have 100 m plus mt all over capital M plus n equals to t. So this is the expression which we were asked to derive. That was the expression we were actually asked to derive. Okay, so I've actually derived it. So that is the expression there. Okay, so this is our second question that I have actually solved. So I think I'm going to end this class at this junction, at this point. So thank you for joining us, and in case you've not subscribed yet, go ahead and subscribe and like the video. If you have any questions, drop them. If you need the materials, just let me know and I'm going to forward it across to you. Although in the material there was an error somewhere in this question. There's an error somewhere, so please use the video to correct that error. Thank you, and God bless you. Hello and good day. This is Samuel and welcome you. So thank you for joining us today in this lesson. Really appreciate your joining us. And please, like I said, if you're not subscribed, go ahead. Make sure you go ahead to subscribe. Make sure you go ahead to subscribe to the video. And you can connect with me via my social media handles on WhatsApp. This is my WhatsApp number. On Instagram, this is my Instagram username. So please subscribe, click on the bell icon so that you always be notified whenever I upload a new video, and share it with your friends as well. And watch out for the next lesson. Watch out for the next lesson. In the next lesson, we're looking at calculations of specific heat capacity involving the electrical method. So thank you and bye.